Hello. In this video, I'll be going over AICE Physics Syllabus Code 9702, Paper 22 from May-June 2017. Right now, we're focused on waves, and so question 4 here, if you want to attempt that one as a review, go for it. If there's a request to see that calculation worked out, I'm certainly happy to do so, but I'm going to focus on question number 5 for right now. It reads, define the frequency of a sound wave. Well, one thing that we should know is that a sound wave is a longitudinal wave, and so, perhaps that's important to keep in mind as we define, but just frequency of a wave is defined as the number of oscillations per second. The number of oscillations, and we'll just say per unit time. So the unit time is a second. So number of oscillations per unit time is the frequency of a sound wave. And so sound being longitudinal, the particles are oscillating parallel to the direction of propagation of energy. They're moving backwards and forwards, however many times, per second, the frequency of that sound wave. Part B says, a sound wave travels through air. Describe the motion of the particles relative to the direction of travel of the sound wave. And so that explanation I just gave a moment ago would go down here. The motion of the air particles is going to be parallel to the direction of travel of the sound wave. The motion of the air particles is parallel to the direction of travel of the sound wave. I always try to parallel the language of the question as much as I can to keep my wording precise. Parallel for a longitudinal wave, sound is a longitudinal wave. The question goes on to give us some practice with cathode ray oscilloscope. So one of the learning outcomes is to be able to determine the frequency, which is what we're going to have to do here from a cathode ray oscilloscope. And so this is a good worked example for trying to master that learning outcome. The question says, the sound wave emitted from the horn of a stationary car is detected with a microphone and displayed on a cathode ray oscilloscope, or c.r.o, as shown in figure 5.1. The y-axis setting is 5 millivolts per centimeter. The time base setting is 0.50 milliseconds per centimeter. Use figure 5.1 to determine the frequency of the sound wave. So a cathode ray oscilloscope is a way to sort of convert the sound wave into a voltage, which can then be, read out on a graph in front of us, and we can read off how much time each centimeter of space in this case represents. Half of a millisecond for every centimeter. So we find an entire waveform occupies this much space, and each one of these squares here is 1 centimeter. So 1, 2 is half a wave, so 3, 4 centimeters makes an entire wave. So it's important to just kind of write out kind of what we know here, that we've got 4 centimeters per wave. And maybe we could rewrite that the other way. Let's sort of think about where we're going with this. We want to know the frequency of the sound wave. And so typically we're going to be able to use the time-based setting to give us a time or the period of the wave. So if we know that the time-based setting is 0.5 milliseconds per centimeter, and we know that there are 4 centimeters per wave, then when we solve this, we're going to cancel out centimeters and we'll have milliseconds per wave. That would be the time period of the wave. Remember that a millisecond is the same thing as 0.5 times 10 to the negative 3 seconds. So we can multiply that by 4 to get the time period. 0.5 times 10 to the negative 3 times 4. So the time period of the wave is 0.002 seconds. Time equals 0.002 seconds. And frequency is 1 over time. And so we can use the inverse to calculate the frequency 500 hertz. It then says, the horn of the car sounds continuously. Describe the changes to the trace seen on the c.r.o. as the car travels at constant speed. So keeping with the theme of, blaring car horns and, blowing whistles and blasting speakers, this is a Doppler effect question, right? And so now we are to describe the changes to this trace that are seen on the cathode ray oscilloscope as the car is traveling at constant speed towards the microphone and then away. So remember, this is where we use the Doppler effect equation, and we are going to subtract in the denominator when we're moving towards, and we're going to add in the denominator when we're moving away. The Doppler effect equation is one of the equations, as you may recall, provided to you on the list of formula as you sit for the AICE Physics Papers 1 and 2. We don't really need to do a calculation here, but just sort of keep the concepts in mind as to what's going to happen. And remember that the question asks us to describe changes to the trace here. So there's really going to be two effects. One is that the Doppler effect is going to make it such that the waves are going to be occurring more frequently, and so we're going to be able to fit sort of more waves onto this cathode ray oscilloscope. It will look like the wavelengths are getting closer together, but remember, we're not looking at wavelength, we're converting, sort of the time of the wave into a length. That's what the oscilloscope does. We want to make sure that we are answering the question, and so when we're moving towards the stationary microphone, one effect will be the waves occur more frequently. That is to say, the time period gets shorter, right? So they occur more frequently because the time, so as the frequency goes up, the time period decreases. The other effect as we speed towards a microphone is that the y-axis here is converting sort of the amplitude is the height of this wave, and that's related to the intensity. And intensity, human perception, is loudness, and so we'll see that the amplitude of this wave is also going to increase as we get closer and closer to the microphone. So that's going to be an additional effect. The amplitude of the wave will increase. That's another change to the trace that we'll see. So we'll see that these waves are going to sort of get squashed together, appear more closely, and the height of the wave, the amplitude, will also increase. And so as the car travels at constant speed directly away from the stationary microphone, the waves occur less frequently. The frequency decreases. That is to say, the time period increases. Likewise, the amplitude of the wave, rather than increasing, is going to decrease because it's speeding away from the microphone, and so it's going to get less and less loud. And that's just sort of intuitive. Things are less loud the further away they are. The amplitude of the wave will decrease.